Hello and welcome to Big Day in Education. I'm Ryan Baker. Today we're going to talk about the Q matrix. What is the Q matrix? It has nothing to do with Keanu Reeves. It's a table where each row is an item and each column is a skill. People also call this by other names, including a KC, knowledge component model, or a skill item mapping. So if we look at an example of a Q matrix, and you see one here, you got a set of items, you got a set of skills, and you can see that item 1 involves skill 1. Item 2 involves skill 1 and skill 2. Item 3 involves skill 1 and skill 3, and so on. Every item involves at least one skill. If an item didn't involve any skills, then we'd need to create a new skill for that. So let's take an example. Let's say that these are your items and these are your skills. So 7 plus 3 plus 2 involves addition, but not subtraction, multiplication, or division. 7 plus 3 minus 2 involves addition and subtraction. 7 plus 3 times 2 involves addition and multiplication. And you could say there are other skills involved here too, like order of operation, but that's not in this set. How do we get this skill item mapping? Well, there's 3 things people do to get to it. They do automatic model discovery, hand development and refinement, and hybrid approaches. We'll talk about automatic model discovery and hand development and refinement today. We'll talk about hybrid approaches in the next lecture. So automatic model discovery. What you do there is you learn the mapping between items and skills solely from data. One popular algorithm is by Barnes, Bitzer, and Vuk. I'll talk about that one today. Now, this is not the only approach to doing this. Non-negative matrix factorization is an alternative. It's got a heck of a lot of linear algebra. If you want to learn more, I recommend reading this paper. So now let's talk about Barnes et al.'s algorithm. The first question is, how many skills should we use? Should we try 3 skills, 78 skills? This is actually determined empirically. Everything's empirical in this algorithm. We try 1 skill, and then we try 1 more skill than the previous model, which after 1 is 2. And if the 2 skill model does better than the 1 skill model, then we go back and try the 3 skill model. 3 skill model is better than 2, we try the 4 skill model. We keep trying this until nothing gets better. And after that, we just follow the pseudocode, which I think is pretty self-explanatory. And any questions? All right, let's actually break that down. What does that algorithm say? Instead of going through the pseudocode, let's discuss what it means. So first of all, for each number of skills, the algorithm is going to be run a certain number of times with a different random initial assignment of items to skills. And this avoids local minima, which we talked about earlier when we talked about the EM algorithm and brute force when we were talking about BKT. So we start with the first random version, completely random about how we assign items to skills. And then the second random version, totally different. We're going to do the whole process for each of these random versions. And they should have no connection to each other except that they have the same number of skills. Next, we take a set of passes through the table. So we're going to look at every single cell in the table, every single row and column, and we're going to systematically look at whether flipping each 1 to 0 and each 0 to 1, in other words, saying this skill doesn't actually involve this item or this item does involve this skill, see whether this produces a better model. We continue this process a predetermined number of times, a maximum number of iterations, or until a pass results in no changes. So how do we know if it's a better model? I kind of left that vague, right? There's several different definitions. The definition that Barnes and colleagues use is that a better model has the property that if a student knows skill X and item 1 and item 2 both involve skill X, then a student who gets item 1 right is going to be more likely to get item 2 right. And if a student gets item 1 wrong, they'll get item 2 wrong. And if they get item 2 right, they'll get item 1 right. And if they get item 2 wrong, they'll get item 1 wrong. So in other words, performance on 2 items that involve the same skill should be connected. To put it another way, given a skill item mapping, you can predict for each combination of skills whether a student should get each item correct or not. And a model's degree of error is based on how many item student pairs the prediction gets wrong. So there's a subtlety. Is the skill conjunctive, as in Barnes, which means if an item has multiple skills, you need every relevant skill to get an item right. If an item involves skills 1, 2, and 3, you need to have 1, 2, and 3 or you're going to get it wrong. Or is skill compensatory, as Zach Pardos proposes, where having any relevant skill leads to getting an item right. In other words, if you have skill 1 or 2 or 3, any one of them, you're going to get the item right. It's also worth noting that the exact approach in Barnes et al. Assumes no learning. In other words, if item 1 and item 2 both involve the same skill, and you take item 1, you will not be any more likely to get it right or wrong on item 2, given having done item 1. Item 1 and item 2 are correlated, but it's not like doing item 1 then makes you better at item 2, or doing item 2 then makes you better at item 1. You're not getting better over time. It's like IRT, not like BKT. An alternate test of model goodness is to look at student improvement over time. You fit a model like PFA or BKT from earlier in week 4 and see how well it fits data given the skill item mapping. More on this in a second. So the second approach we're going to talk about is hand development and refinement. This is the original way that Q matrices were created, actually. A domain expert, really smart person, creates the Q matrix using knowledge engineering, which we discussed last week. So what kind of data can we use to guide refinement? I'm actually going to give some slides with permission that John Stamper gave a talk in my class on. So 3 strategies that John talked about are, first, try to smooth learning curves. This is actually a strategy that comes from Corbett and Anderson in '95. Second, look for skills with no apparent learning. And third, look for problems with unexpected error rates. There's a tool for doing this, and it's called the Pittsburgh Science Learning Center Data Shop. You can also do it in Excel, you can do it in a visualization program, but the Data Shop's got tools to help you do it. It's a great program. I love Data Shop. The learning curve shows the relationship between the student's amount of practice, the number of opportunities the students had to demonstrate or to learn a skill, and their performance. So on the x-axis, we have how many opportunities the student has to learn the rule. On the y-axis, we have the error rates. Incidentally, this classic graph comes from Corbett and Anderson '95. And you can see that the error rate goes down as the student practices more, and you kind of hope that would be what happens. Now, spikes in learning curves often imply that 2 or more skills are being treated as a single skill. So if we look at this graph, the student seems to be getting better, then they shoot up, then they come down, then they shoot up again. And actually, this graph actually is demonstrating 2 different learning curves occurring. If you look at its 2 learning curves, it looks really smooth and nice. But if you look at it like one, it's a total mess. The PSLC Data Shop makes it possible to look at learning curves for different skill models. So for example, if you treat geometry area as a single skill, the entirety of geometry area, you don't get a smooth learning curve. But if you split it into the 12 component skills, then you get a smooth learning curve shown at the bottom right. You can actually inspect curves for individual skills. Again, this is pictures from the Data Shop. Thanks again to John for providing these. And you see that many curves show a reasonable decline, that is, less errors over time. There's a little spikiness. You're going to get that if you don't have much data. But some don't, and that's actually an opportunity to improve your model. If you have a skill that's not going like this, then either you're teaching it really badly or your model's messed up. Possibly both. The second thing you can do is look for problems with unexpectedly high error rates. There's a tool in the Data Shop called the Performance Profiler, shown here, where it shows you each item's actual error rate and the predicted error rate based on the model. If you've got an item that has an error rate that's much higher than what you'd predict from the model, you know there's something wrong there and it's something worth looking at. Maybe that problem doesn't fit the skill you think it does. So once you've built a skill item mapping, the Data Shop can actually test how good it is for you. It applies a mathematical model called LFA, which is similar to PFA, to the data, and then gives you AIC and BIC goodness measures for the different skill item mappings you might have created. So Data Shop's a useful tool for this kind of thing if you want to do hand model refinement and development. In the next lecture, I'm going to talk about knowledge structure inference, hybrid approaches, and models with prerequisites and hierarchy. So see you next time. I'm Ryan Baker. This is Big Data Education. Thank you very much.